AWS. VPC versus GCP. VPC versus Azure VNet. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. In this series, we are going to do a deep dive comparison of the three most dominant cloud providers and the way each one implements virtual private networking. The concept of isolating your workloads inside a logically private network is fundamental to every enterprise cloud deployment, and yet Amazon AWS, Google Cloud Platform, and Microsoft Azure have each taken subtly different architectural approaches to solving the same problem. Understanding these differences is not merely academic. When you are designing multi-cloud architectures, migrating workloads between providers, or sitting for a professional certification exam, you need to know precisely how each cloud draws the boundaries of a virtual network, how it handles routing, and where its limitations and advantages lie. Over the next set of slides, we will introduce the core concepts, walk through each provider in detail, and then build a structured comparison across dimensions such as geographic scope, subnet design, routing, security layering, and hybrid connectivity. By the end of this series, you will be able to confidently discuss and architect virtual networking across all three platforms. AWS VPC Overview. Amazon Web Services introduced the Virtual Private Cloud in 2009, and it has since become the reference architecture against which other cloud networking models are measured. The AWS VPC is a regional construct, which means every VPC you create is bound to exactly one AWS region such as US East 1 or EU West 2. It cannot span multiple regions natively. Within that region, the VPC spans all availability zones. An availability zone is an independent data center or cluster of data centers within the same region, designed to be isolated from failures in other availability zones. This is a critical design detail. When you create a subnet inside a VPC, you must pin it to a specific availability zone. Traffic between subnets in different availability zones within the same VPC is routed locally and does not leave the AWS network, but it does cross AZ boundaries, which carries a small data transfer cost. You define the IP address space for a VPC using a CIDR block in RFC 1918 private address space. The smallest VPC CIDR block is a /28, which gives you 16 IP addresses, and the largest is a /16, which gives you 65,536 addresses. AWS reserves 5 addresses in every subnet for internal purposes, so the actual usable count is always 5 fewer than the mathematical total. The diagram on this slide illustrates how a single AWS region contains multiple availability zones, and how a VPC with a /16 CIDR is subdivided into subnets, each anchored to an AZ. This regional and AZ-aware design forces architects to think explicitly about high availability from the very first network design decision. Google CP VPC Overview. Google Cloud Platform took a fundamentally different architectural approach when designing its virtual private cloud. The most important distinction to understand immediately is that a GCP VPC is a global resource. Unlike AWS, where a VPC is confined to a single region, a single GCP VPC spans all regions simultaneously. This means a VPC you create in your GCP project is automatically present in US Central 1, EU West 1, Asia Pacific East 1, and every other region without any additional configuration. This global nature has profound implications for multi-region architectures. In AWS, if you want workloads in 2 different regions to communicate privately, you must either create 2 separate VPCs and connect them via VPC peering or transit gateway, or use other overlay mechanisms. In GCP, those workloads simply live in subnets within the same VPC, and GCP's internal backbone carries the traffic between regions without any additional peering constructs needed. However, subnets in Google CP are regional resources. Each subnet is associated with a single region, and you specify the primary CIDR range for that subnet when you create it. This means the global VPC contains regionally scoped subnets, and virtual machine instances connect to a specific regional subnet. Google CP also supports secondary IP ranges on subnets, which is heavily used by Google Kubernetes Engine to give pods their own IP addresses without requiring additional subnets. Google CP VPCs also have two modes: auto mode and custom mode. Auto mode automatically creates a subnet in every region with a predefined /20 CIDR block from the 10.128.0.0/9 range. Custom mode gives you complete control and is strongly recommended for production environments because it prevents IP address overlap and gives you precise control over your addressing scheme. The diagram shows how the global VPC boundary contains subnets distributed across multiple regions, all within a single VPC object. Azure VNet Overview. Microsoft Azure's equivalent of a virtual network is called a virtual network, abbreviated as VNet. Like an AWS VPC, an Azure VNet is a regional resource, meaning it exists within a single Azure region such as East US, West Europe, or Southeast Asia. It cannot span regions natively. A fundamental architectural difference in Azure is how subnets are structured. In AWS, subnets are availability zone specific. In Azure, subnets within a VNet are not bound to specific availability zones. When you deploy a virtual machine and select an availability zone, Azure handles the AZ placement at the compute layer, while the subnet itself is available across all AZs within the region. This is a more flexible model for subnet design, as you do not need to create parallel subnet sets for each AZ. However, it means you must design your compute deployment strategy to ensure AZ spread rather than having the network enforce it. Azure VNets use address spaces defined in CIDR notation, and you can add multiple non-overlapping address spaces to a single VNet after creation, which is useful when you need to expand your network without recreating it. Each subnet then carves out a portion of one of those address spaces. Azure reserves 5 IP addresses in every subnet, the same as AWS. Azure also has a concept called VNet integration, which allows Azure Platform as a Service services such as Azure App Service, Azure Functions, and Azure API Management to be joined to a VNet so that they can reach resources on your private network. This integration model differs from GCP and AWS, where equivalent functionality is achieved through private endpoints or VPC endpoints. The diagram illustrates the VNet regional boundary, the non-AZ pinned subnets, and the relationship to the broader Azure resource hierarchy including subscriptions and resource groups. Geographic scope comparison. One of the most architecturally significant differences between the three cloud providers is how they define the geographic boundary of a virtual network. This single decision cascades into implications for multi-region design, routing complexity, and operational overhead. Looking at the diagram, we can trace the boundary for each provider. AWS places the VPC boundary at the regional level. A VPC in US East 1 is completely separate from a VPC in US West 2. To connect workloads across regions in AWS, you use inter-region VPC peering or AWS Transit Gateway with inter-region peering attachments, both of which incur additional data transfer costs and require explicit route configuration. Google Cloud Platform draws the VPC boundary at the global level. A single VPC spans all regions, and subnets within that VPC are regional. Two virtual machine instances in different regions but within the same VPC can communicate using private IP addresses over Google's global fiber backbone. No explicit peering or routing constructs are required. Google Cloud Platform's internal routing is advertised globally within the VPC based on dynamic routing mode. Regional mode only advertises subnet routes within the same region, while global mode advertises all subnet routes across all regions. For multi-region workloads, global dynamic routing mode is essential. Azure sits in the same camp as AWS. A VNet is regional. Cross-region private connectivity in Azure is achieved through global VNet peering or Azure Virtual WAN, which is Microsoft's managed transit networking service for interconnecting VNets, on-premises sites, and Azure services at scale. The table on this slide summarizes these differences side by side. From a design standpoint, the Google CP Global VPC model reduces the operational complexity of multi-region architectures but requires more careful subnet IP address planning upfront to avoid address exhaustion across all regions in a single site or space. AWS and Azure's regional model provides cleaner regional isolation at the cost of additional peering and routing configuration for cross-region traffic. Subnet design comparison. Subnet design is where the three cloud providers reveal additional architectural differences that directly affect how you plan your IP address space and where you deploy your workloads for high availability. In AWS, subnets are scoped to a single availability zone. This is by design. It forces you to create separate subnets per AZ for each tier of your application. A standard 3-tier highly available deployment in AWS with 2 AZs would require at least 6 subnets. A public subnet in AZ-A, a public subnet in AZ-B, an application subnet in AZ-A, an application subnet in AZ-B, a database subnet in AZ-A, and a database subnet in AZ-B. This approach makes AZ placement explicit and auditable from the network configuration alone, but it requires more planning and consumes more of your CIDR space for subnets. In GCP, subnets are regional. A single subnet spans all zones within its region. You deploy a virtual machine instance into a zone and it receives an IP from the regional subnet. This means a 3-tier highly available deployment in GCP with 3 zones still uses just 3 subnets, 1 per tier, each spanning all zones. The zone placement decision is made at the compute layer, not the network layer. This simplifies subnet management but means the network layer no longer acts as an enforcer of AZ discipline. Azure subnets are also not AZ-pinned, behaving similarly to GCP subnets in that they span all availability zones within the region. Zone placement is handled at the compute and storage resource deployment level. The diagram on this slide maps these subnet scoping models side by side across the 3 providers, clearly showing how AWS requires AZ-specific subnets while GCP and Azure use broader regional subnets. Understanding this difference is critical when migrating workloads between clouds, as your AWS subnet architecture will not translate directly to a GCP or Azure subnet design. Routing models. Overview. Routing is the mechanism by which a cloud virtual network decides where to send a packet based on its destination IP address. Each of the 3 cloud providers implements routing differently, and understanding the model for each platform is essential for diagnosing connectivity problems and designing networks that behave predictably. The common thread across all 3 providers is that routing is handled by the software-defined control plane rather than by physical routers. Every virtual network has a set of implicit or system-managed routes that are created automatically, and you can supplement or override these with custom routes you define yourself. Looking at the diagram, each provider starts with a set of system routes that cover local subnet to subnet communication and provide default routes toward the internet. On top of that base, you can inject custom static routes or, in the case of dynamic routing using BGP, have routes learned automatically from on-premises networks or from VPN and dedicated interconnect attachments. The key differences lie in where route tables live, how they are associated with subnets, and how transitive routing is or is not supported natively. AWS and Azure use route tables that are explicitly associated with subnets. GCP uses a flat routing model where routes are applied at the VPC level and filtered to specific instances using network tags or route applicability settings. These architectural differences create different operational workflows for network engineers and have meaningful implications for how you implement hub and spoke topologies, forced tunneling, and traffic inspection. GCP routing, deep dive. Google CP's routing model is fundamentally flatter than AWS or Azure. Rather than associating route tables with individual subnets, Google CP applies routes at the VPC level and uses a route applicability mechanism to determine which virtual machine instances a given route applies to. This distinction is significant. In Google CP, you do not configure a subnet and then attach a route table to it. Instead, every route has an optional network tag filter. If a route has no network tag specified, it applies to all instances in the VPC. If a route specifies a tag like private egress, it only applies to virtual machine instances that have that tag assigned to them. Google CP automatically creates system-generated routes for every subnet you add. These subnet routes cover the primary CIDR and any secondary CIDRs of the subnet and ensure intra-VPC communication works without additional configuration. These system routes cannot be deleted as long as the subnet exists. When GCP dynamic routing mode is set to global, a cloud router in one region learns BGP routes from an on-premises network via Cloud VPN or Cloud Interconnect, and those learned routes are propagated to virtual machine instances in all regions of the VPC. This is a powerful capability that has no direct equivalent in AWS without Transit Gateway, and it eliminates the need to deploy separate VPN or interconnect attachments in every region that needs on-premises connectivity. The diagram shows how a virtual machine instance in a private subnet that carries the tag private egress matches the custom route pointing to the CloudNAT and Cloud Router for outbound traffic, while a virtual machine without that tag uses only the default routes. This tag-based routing model provides very granular control over which instances follow which paths without requiring separate subnets. Security layer comparison. Security filtering in virtual networks is implemented through layered controls, and each cloud provider offers a somewhat different set of primitives with different scoping, statefulness, and evaluation models. Understanding where each layer sits in the traffic path and what it can and cannot do is essential for building a robust security posture. The table on this slide summarizes the key dimensions across all three providers. Let me walk through each row. The first dimension is statefulness. AWS security groups and Azure NSGs are both stateful, meaning that if an inbound connection is allowed, the corresponding outbound return traffic is automatically permitted without requiring an explicit outbound rule. AWS network ACLs and GCP firewall rules are the outliers here. Network ACLs are stateless, so you must explicitly configure both inbound and outbound rules for each permitted flow. GCP firewall rules are stateful, which simplifies rule management. The second dimension is attachment scope. AWS security groups are attached to individual elastic network interfaces, making them the most granular enforcement point. Network access control lists apply to entire subnets. Google CP firewall rules apply to the VPC and target specific instances using network tags or service accounts. Azure NSGs can be applied at both the subnet level and the NIC level simultaneously, creating two enforcement checkpoints for the same traffic. The third dimension is rule type. AWS security groups support only allow rules. Network ACLs support both allow and deny. GCP firewall rules support both allow and deny at the VPC level, and hierarchical firewall policies at the organization and folder level add additional allow and deny capabilities that override project-level rules. Azure NSGs support both allow and deny rules with numeric priority ordering from 100 to 4096, where lower numbers are evaluated first. The fourth dimension is default behavior. All three providers implement an implicit deny for traffic that does not match any explicit allow rule, which is the correct zero-trust starting posture for any secure network design. GCP firewall rules, deep dive. Google CP's firewall model is architecturally different from both AWS and Azure in a fundamental way. Firewall rules are not attached to subnets or network interfaces at all. They are applied at the VPC level and then targeted at specific virtual machine instances using one of two targeting mechanisms: network tags or service accounts. This design decouples your security policy from your network topology, which is a significant conceptual shift if you are coming from an AWS or Azure background. A GCP firewall rule consists of several key attributes. The direction field specifies whether the rule governs ingress traffic coming into a virtual machine or egress traffic leaving a virtual machine. The priority field is a number from 0 to 6, 5, 5, 3, 4, where a lower number means higher priority. The action field is either allow or deny. The source or destination is specified as IP ranges, tags, or service accounts. The protocol and port combination specifies what traffic the rule matches. And the target specifies which virtual machine instances the rule applies to via network tags or service accounts. Network tags are simple string labels that you assign to virtual machine instances. A firewall rule that targets the tag web server applies to every virtual machine in the VPC that carries that tag, regardless of which subnet, region, or zone the virtual machine is in. This global tag-based targeting is extremely flexible for policies that need to follow application roles across a distributed environment. Service account-based targeting is even more powerful because service accounts are cryptographically bound to virtual machine identity. A firewall rule that targets instances running as service account A cannot be spoofed by an attacker who simply adds a tag to a compromised instance. This makes service account-based firewall rules the recommended approach for sensitive workloads. Hierarchical firewall policies, introduced as GCP's organization-level security governance layer, allow security teams to define firewall rules at the GCP organization or folder level that are evaluated before any VPC-level rules. This enables a centralized security team to enforce mandatory deny rules across all projects in the organization while still allowing project teams to manage their own additional allow rules within the governed boundaries. Hybrid connectivity. Overview. Hybrid connectivity refers to the ability to establish private network paths between your cloud virtual network and your on-premises data centers, branch offices, or other cloud environments. For most enterprise deployments, the cloud is not a replacement for on-premises infrastructure but an extension of it, and the quality, reliability, and security of the connection between the two environments is critical. All three cloud providers offer two fundamental categories of hybrid connectivity. The first is IPsec VPN, which creates an encrypted tunnel over the public internet between your on-premises VPN device and a cloud-side VPN gateway. VPN connections are quick to provision, relatively inexpensive, and do not require dedicated physical infrastructure, but they are subject to the variable latency and bandwidth constraints of the public internet. Most providers support BGP over VPN for dynamic route exchange, which eliminates the need to manually maintain static routes on both sides of the tunnel. The second category is dedicated private connectivity, which provides a physical circuit between your facility and a cloud provider's edge location. AWS calls this Direct Connect. GCP calls it Cloud Interconnect. Azure calls it Express Route. These dedicated circuits offer predictable low latency, high bandwidth up to 100 gigabits per second in some configurations, and traffic that never touches the public internet, which is mandatory for many regulated industries. The trade-off is higher cost, longer provisioning times, and the need to work with a colocation or carrier partner. The diagram on this slide shows the common conceptual model shared across all three providers. An on-premises edge router connects either via an encrypted VPN tunnel over the internet or via a dedicated private circuit through a colocation facility to the cloud provider's edge, which then connects to the virtual network gateway and into the VPC or VNet. AWS Hybrid Connectivity, Direct Connect and VPN. AWS Site-to-Site VPN creates an IPsec VPN connection between your on-premises customer gateway device and a virtual private gateway or transit gateway on the AWS side. Each site-to-site VPN connection actually consists of two parallel IPsec tunnels terminating in different AWS availability zones, providing built-in redundancy. You should configure your customer gateway to use both tunnels simultaneously for active-active operation, or at minimum keep the second tunnel in hot standby. AWS VPN supports both static routing and dynamic BGP routing. With BGP, your on-premises router and the AWS Virtual Private Gateway Exchange routes automatically, making route management much simpler in environments with many prefixes. AWS Direct Connect is a dedicated private network connection between your facility and an AWS Direct Connect location. AWS has over 100 Direct Connect locations globally, which are colocation facilities where AWS has deployed network equipment. To use Direct Connect, you either collocate your equipment in the same facility and cross-connect directly to AWS, or you work with an AWS Direct Connect partner who provides a hosted connection from their facility to yours. Direct Connect connections come in speeds of 1 gigabits per second, 10 gigabits per second, and 100 gigabits per second for dedicated connections, or as low as 50 megabits per second for hosted connections through partners. A Direct Connect gateway is a globally available resource that allows a single Direct Connect connection to reach VPCs in multiple AWS regions. Without a Direct Connect gateway, a Direct Connect connection can only reach VPCs in the same region as the Direct Connect location. With a Direct Connect gateway, you attach virtual private gateways from VPCs in different regions and reach all of them over a single physical connection. The diagram shows an on-premises network connecting to AWS through both a site-to-site VPN for redundancy and a Direct Connect connection for primary traffic. The Direct Connect gateway connects to virtual private gateways in two different regions, allowing on-premises users to reach workloads in both US East 1 and EU West 1 over a single Direct Connect circuit. The transit gateway is shown as the central hub for routing between the VPCs and the hybrid connections within a single region. Google CP Hybrid Connectivity, Cloud VPN and Cloud Interconnect. Google CP provides two dedicated hybrid connectivity products that differ from AWS in some important architectural details. The first is Cloud VPN, which supports two modes. Classic VPN is the older mode and supports only static routing or policy-based routing. HAVPN is the newer mode and is strongly recommended because it provides a 99.99% availability SLA and requires BGP for dynamic routing. HAVPN achieves its high availability by creating two VPN tunnels, each terminating on a separate Google-managed gateway interface in different physical redundancy domains. On your on-premises side, you need two tunnel endpoints connecting to both Google CP gateway interfaces to get the full SLA. Cloud Interconnect is Google CP's dedicated private circuit product, equivalent to AWS Direct Connect. It comes in two delivery options. Dedicated Interconnect provides a direct physical connection between your facility and a Google colocation facility, available in capacities of 10 gigabits per second or 100 gigabits per second per circuit, with up to 8 circuits bundled in a link bundle for a maximum of 800 gigabits per second. Partner Interconnect delivers connectivity through a Google CP network service partner when you cannot collocate directly with Google, and it supports capacities from 50 megabits per second up to 50 gigabits per second through the partner. An important Google CP-specific concept is the VLAN attachment, also called an interconnect attachment. When using Cloud Interconnect, you create one or more VLAN attachments on top of the physical circuit. Each VLAN attachment connects to a cloud router in a specific region and carries traffic for a specific VPC. This means a single 100 gigabits per second dedicated interconnect circuit can be subdivided into multiple VLAN attachments of different sizes, each serving a different VPC or different region, maximizing the utilization of the physical link. The diagram shows how an on-premises router connects to both a GCP colocation facility via a dedicated interconnect circuit and to GCP's high-availability VPN gateways for backup. The dedicated interconnect carries VLAN attachments that connect to cloud routers in two different regions, allowing on-premises networks to reach subnets in both regions across the same physical circuit through GCP's global VPC routing. IP addressing comparison. IP address planning is one of the most consequential decisions you make when designing a cloud virtual network, because changing your address space after workloads are deployed is expensive and disruptive. Each cloud provider has specific constraints and capabilities around how you define, expand, and subdivide your IP address space. All three providers support RFC 1918 private address ranges, RFC 1918. All three also support IP version 6, though the implementation details differ. AWS supports IP version 4 only, dual stack IP version 4 and IP version 6, and IP version 6 only subnets. GCP assigns IP version 6 ranges at the subnet level and supports internal IP version 6 for virtual machine to virtual machine communication as well as external IP version 6. Azure supports dual stack VNets where both an IP version 4 address space and an IP version 6 address space are defined on the same VNet. The table on this slide compares the key IP addressing dimensions across providers. The minimum and maximum subnet sizes are important for planning. AWS reserves 5 IP addresses per subnet. The network address, the VPC router address at .1, the AWS DNS server at .2, a reserved address at .3 for future use, and the broadcast address. GCP also reserves 4 addresses per subnet. The network address, the default gateway at .1, a second reserved address at .2 for potential future use, and the broadcast address. Azure also reserves 5 per subnet matching the AWS model. Google CP's secondary IP ranges are a distinctive feature. A single Google CP subnet can have multiple secondary CIDR ranges defined on it in addition to its primary range. These secondary ranges are used heavily by Google Kubernetes Engine. The primary range provides IP addresses for GKE nodes. The first secondary range provides addresses for pods, and the second secondary range provides addresses for services. This consolidates addressing onto fewer subnet objects, simplifying management compared to the AWS approach of creating separate subnets for each purpose. DNS in GCP VPC. Google CP provides DNS resolution inside a VPC through its metadata server, which is the Google-managed DNS resolver available at the linked local address 169.254.169.254 or equivalently at the virtual IP 8.8.8.8 within the context of the VPC. By default, all virtual machine instances are configured to use this resolver, which handles both public DNS resolution and resolution of names within Google CP's internal DNS namespace. Google CP automatically creates internal DNS records for every virtual machine instance in the format vmname.zone.c.project.id.internal. These auto-generated names resolve to the internal IP address of the instance and are available within the same VPC without any configuration. This automatic internal naming is convenient for small environments but is supplemented by Cloud DNS for production architectures with custom domain requirements. Cloud DNS private zones work similarly to Route 53, private hosted zones. You create a private zone for a domain such as internal.mycompany.com and associate it with one or more VPC networks. Any virtual machine in an associated VPC can resolve names in that zone. Cloud DNS also supports DNS peering between zones, which allows a VPC to resolve names defined in a private zone associated with a different VPC without creating a direct VPC peering relationship. This is useful when a centralized DNS VPC manages shared zones and service VPCs need access to those records. DNS server policies in GCP configure inbound and outbound DNS forwarding. An inbound DNS policy creates a set of regional IP addresses inside your VPC that on-premises DNS resolvers can forward queries to, similar to ROT53 inbound endpoints. An outbound DNS policy defines forwarding rules that send queries for specific domains to on-premises DNS servers, similar to ROT53 outbound endpoints and forwarding rules. The diagram maps the GCP DNS resolution path from a virtual machine query through the metadata resolver to either a cloud DNS private zone, a DNS forwarding rule for on-premises domains, or the public Internet DNS system for external names. VPC and VNet peering comparison. Peering is the mechanism used to connect two virtual networks so that resources in each network can communicate using private IP addresses without traversing the public Internet. All three cloud providers offer peering, but the scope, transitivity, and operational model differ in important ways. AWS VPC peering creates a one-to-one private connectivity relationship between two VPCs. The peering can be between VPCs in the same AWS account, different accounts, or different regions. An important constraint is that the CIDR blocks of the two peered VPCs must not overlap. If they do, the peering cannot be established. Each peering relationship requires ROT table updates in both VPCs to send traffic for the peer's CIDR through the peering connection. AWS VPC peering is non-transitive. If VPC appears with VPCB and VPCB peers with VPCC, traffic from VPCA cannot reach VPCC through VPCB. A direct peering between A and C is required. Google CP VPC peering also creates one-to-one relationships between VPC networks, and it too is non-transitive. One distinctive Google CP behavior is that peered networks exchange all subnet ROTs by default, but you can configure custom ROT export and import settings to control exactly which ROTs are shared across the peering. Google CP peering also supports importing and exporting custom static ROTs across the peering link, which AWS VPC peering does not support for non-default ROTs without additional configuration. Azure VNet peering works similarly and is also non-transitive by default. Azure supports both regional peering within the same region and global peering across regions. A useful Azure-specific feature is the Use Remote Gateways option in peering settings. This allows a spoke VNet to use the VPN gateway or Express ROT gateway deployed in a peered hub VNet for hybrid connectivity, avoiding the cost and complexity of deploying a gateway in every spoke VNet. The table on this slide summarizes peering limits, transitivity, cross-account and cross-region support, and gateway transit capabilities across all three providers. Comprehensive feature comparison matrix. We have now covered a wide range of architectural dimensions across all three cloud providers. This slide brings all of those dimensions together into a single consolidated comparison matrix so you can see the full picture at a glance and use this as a reference during design discussions or exam preparation. Looking at the first section of the table covering network scope and structure, the global versus regional VPC distinction stands out as the most architecturally significant difference. GCP's global VPC means that a single network object manages addressing and routing across all regions, while AWS and Azure require separate virtual network objects per region. For subnet design, AWS is the only provider that enforces availability zone pinning at the subnet level, which makes high availability planning more explicit but also more verbose in terms of subnet count. In the security section, the most notable distinction is Google CP's use of VPC-level tag-based and service account-based firewall rules versus the subnet and NIC-level NSG model in AWS and Azure. Google CP's approach is more flexible for dynamic environments where virtual machine roles change, while the AWS and Azure models provide clearer subnet-level boundaries that are easier to audit in traditional network security frameworks. In the Transit and Connectivity section, AWS Transit Gateway and Azure Virtual WAN both provide full mesh VPC transit with sophisticated routing policy controls. GCP's equivalent for inter-VPC routing remains peering-based rather than hub-based, with NCC focused on hybrid on-premises connectivity aggregation rather than VPC to VPC transit. In the DNS section, all three providers support private hosted zones, DNS forwarding to on-premises, and auto-registration of virtual machine records. Azure DNS Private Resolver stands out as the most recently matured fully managed solution that eliminates the need for custom DNS server virtual machines. GCP's DNS server policies and AWS Route 53 Resolver endpoints serve equivalent purposes with slightly different configuration models. Summary and key takeaways. We have completed our deep dive comparison of virtual networking across AWS, Google Cloud, and Azure. Let me close with the most important architectural principles to carry forward. The choice of cloud provider for virtual networking is not simply a matter of feature checklists. It is about which architectural model aligns best with your organization's existing topology, team expertise, and long-term growth strategy. If your workloads are predominantly single region or if you need very strong regional isolation boundaries, AWS and Azure both provide clear, well-understood regional VPC and VNet models. AWS leads in ecosystem maturity, the breadth of VPC native service integrations, and the sophistication of transit gateway route segmentation. Azure leads in enterprise Active Directory integration, hybrid identity-aware networking, and the integration of network security policy with Azure Policy for governance at scale. If your architecture is inherently multi-regional and you want to minimize the complexity of cross-region routing, Google CP's Global VPC is a genuine differentiator. A single VPC spanning all regions, combined with global dynamic routing mode and Google's own private fiber backbone for inter-region transit, can dramatically simplify multi-region private network design compared to the equivalent architecture in AWS or Azure. The diagram on this slide maps the decision dimensions we covered as a mind map, grouping the key factors under each provider to help you quickly recall the defining characteristics of each platform's networking model during design reviews and technical discussions. Thank you for your attendance. Please consider subscribing to the channel and liking this video.